and then we'll continue with the next lecture. All right, I think I said that I will modify this, so I'll do it. I'll actually remove the whole thing. Okay. All right, slideshow from beginning. So this is the Signals and Systems course. The course will consist of 3 main parts: signals, systems, and transforms. So the first part will be focusing on signals alone. So here are just the learning outcomes. They will be seen also in the syllabus. Right. So basically we'll focus on a few points. This course, actually, the major, let's say, credit will go to they call it the transforms. We have Laplace, we have Z transform, we have Fourier. At the beginning, we'll apply sampling theorem to go from continuous into discrete, or what we call analog into digital. Okay, and we will do a lot of signal manipulations in the form of shifting, scaling, time reversal, etc. So there are plenty of signal manipulation techniques that we can apply on the signal, both in time and frequency domain, but most of the focus will be in time, and we'll see their effect on frequency domain. And there will be a dedicated lecture actually for signal properties and system properties, linear time invariant systems. We'll know, like most of the signals, they are desired to be LTI or linear time invariant systems. And one of the main processes that we'll be dealing through this course is called convolution. It's somehow in concept is similar to multiplication, but it's something we call multiply and accumulate or multiply and add. All systems that we see in life, they process the signals through convolution. All right, so we'll do some analysis on differential equations, and difference equations are differential equations, but this is in discrete time and this is in continuous time. So just to differentiate between discrete and signal, we call them difference equations in discrete and differential equations in continuous time domain. All right, so the grading scheme is as follows. So we'll have 2 homeworks. Both will weigh 10 marks, and usually when a homework is posted, so you have 1 week to submit. So deadline will be 1 week. 2 quizzes. Due to the nature of the course, everything will be, let's say, what we call written response or essay kind of questions. So there will be a lot of solving. Labs, Engineer Haitham will be dealing with the labs. So the labs part consists of 6 practical assessments, and at the end, Alaikum Salam. At the end, you do a project. The project will worth 12 or 15 marks. I will say 15 or 12.5 marks. So out of this 25, consider 50% of this 25 will be gone to the project. And the project will consist of doing a report and a presentation. But yeah, due time, Engineer Haitham will keep you updated. I think at the 10th week you will be having information about the project. Midterm and final, that's the standards 2030. In case you could not make it for a quiz, contact me and we could arrange it. However, midterm and final, they are arranged by the registration department. All right, so here are the association between learning outcomes and the marks. The textbook, I think the slides are enough. Slides and lecture notes will be enough. However, it is encouraged that you have this book, Alan Oppenheim. It has a lot of problems, their solutions, examples, etc. So this is a very suitable book for entry-level course in signals and systems. All right, so we talked last week, every system in life, we have this what we call IPO, input, and we have process, and we have the output. So in time domain, our inputs are usually symboled with x of t. And we have h of t, that's the system response. We'll give it a name in the future, but that's the system behavior. And we have the response, the output. Usually x of t, we can call it also excitation signal or input signal. And y of t is the output or response signals. All right, so that's in continuous time domain. That's what we call an analog or continuous. In digital, we will have x of n. And then here we don't call it like a function, we call it a sequence. And because of its discrete, or to tell it is a discrete, we use the independent variable n, and we use the square brackets. In continuous, we have the regular parentheses. And here the system response will be h of n, and the output y of n. Again, it's all discrete in the digital domain. A typical example, communication systems. In the future, students will take communication systems. This is very common. So you have the information signal, x of t. We'll go through a processor step called the transmitter that will do a process called modulation. So that's a typical communication system here. Don't pay attention a lot into this topic. It's just an example to show you where signals are used. And this signal or modulated signal will be sent over space through a certain channel. The channel could be fiber optic, or it could be free space, or copper wires, like that, many forms, copper wires, many forms of media. And then it will be received at the receiver part. And the main goal is to have x of t as close as to y of t, because you are sending a signal, you're expecting the receiver to have the same signal. However, due to many factors that the signal will go through, like noise, like the information signal will be a little bit noisy. There are a lot of algorithms to reduce that noise or filter out that noise. At the transmitter and receiver parts, we have the thermal noise due to the electron flow and electrical components. And here we have some modeled, what we call it, additive white Gaussian noise. So that's what noise that you have in nature, like thunder or lightning, any kind of noise that you may face. So that's an example of a communication system that use signals. And noise also is considered as a signal, but it's kind of a random signal that is not predicted. All right. So what is a signal? Is anything that covers information. I'll go over it real quick. I've done that last week. So we can divide signals, or we can classify them into independent and dependent variables. Dependent means that you get the value depending on another value here. For example, you have x of t equal 3t minus 2. You will never know the value of x unless you know the value of t. All right, so here x is dependent, and t here, like, is the value given. It does not depend on any other variable, so that's the independent variable. Independent variable. There are many forms of signals. Mostly in our course, we'll be dealing with voltages, or not in our course. In electrical engineering, most of the signals are in the form of voltage or current. In mechanical systems, we have position, velocity, in the fluid dynamics, flow rate. And digital signal processing, we have digital images or an image processing, and also stock market index in finance. All right, so we can classify signal by one-dimensional or multi-dimensional based on the number of independent inputs. So for example, if you have an audio signal, so the x-axis is time, and here is the x of t, that's the audio signal. So here I have only one independent variable, so that's a one-dimensional signal. An image, for example, could be modeled as a matrix, and each index here has a value here. So we have column and a row index, and we have a column index. So we need these values of the row and column to retrieve the information here in that pixel. And here we call it 2D signal or two-dimensional signal. An example of 3D signal, like a video here, and you have, yeah, the rows, you have columns, but you add a third dimension, that's time. So each image is considered like a frame, and you have three-dimensional signal here, 3D. Now, signal could be also classified into continuous and discrete, depending on the dependent variables. So a signal with continuous independent variable is said to be a continuous time signal, like this example here. So here time is continuous and the signal is continuous in time. There are no discontinuities in time. Now there are discrete time signals, something like this. So I have this value here, this value there, etc. So you have at different points in time, and let's say this is 1, 2, 3, 4, and this is what we call a discrete time signal. Okay, so also we can look at the value itself. Here, this signal, there are no discontinuities on the values here. So that's a continuous time signal. Sometimes here with a process called quantization, we'll talk about it later. This signal could be having only a certain set of values, could be 1, 2, 1, etc. So it does not take any other values rather than 1 and 2. All right, so continuous or discrete dependent variables. Okay, we talked about it. So we have analog signal. It's a continuous value signal, like a voltage waveform, something like this. That's a continuous signal. A digital signal is a discrete value, discrete time signal, something like this, like the digital audio. This figure here kind of summarize all four combination, because you have an independent variable and dependent variable. So in this one here, the independent variable is time, so it's continuous time, and the dependent value is continuous time. So you have this combination, continuous time, continuous value signal, like any other signal, like a noisy signal or this kind of a sinusoidal. That's a modulation signal, by the way. So you have what we call an envelope, and you have the signal inside, but there are no discontinuities anywhere. So that's a continuous time signal. This one here, it is discrete in time. So that's a discrete time signal, but you can have any value in here. I'm not restricted by certain levels at the y-axis. So it's discrete in time. So I don't have any value here or there. So it's discrete in time, and in value, it is continuous. You can have any value here. You are not restricted to certain levels. However, this one here, you are restricted into certain levels. So that's a discrete value signal. And there are no discontinuities in time. So that's a continuous time, but discrete in value. Discrete in value, in here, there are no values. In here also, there are no values. We're only looking at these values. Those are transitions. They are not values. They are not considered values. So that's a continuous time, discrete value signal. Another example here, a continuous time, discrete value signal. That's a typical digital signal. You have values either 0 or 1, and they are continuous in time. So both of them actually same example. Here I'm having only what we call a binary value or binary signal, 0 or 1, and here it's what we call quantized signal. You can have 0, 1, 2, 3, and you have -1, -2, for assuming that each spacing is 1. Now also looking at the nature of signals, could be predicted, could be random. So for example, noise, always a random signal. You don't know any information. However, you may model it with certain statistics like mean and variance. So it is continuous in time and continuous in value, like the noisy signal here. So random signal cannot be predicted exactly and cannot be described by any mathematical function. However, let's say, for example, x of t equal sine 2 pi 10t plus 30. So this is what we call a predicted signal. Why? I know that at certain point in time, I can estimate the value of X. That's what we call a predicted signal. So I can determine the value of the signal based at any point in time. However, in here, there is no formula that can model this noise. There is no mathematical expression. All right. So we've seen that already, continuous time signals and discrete time signals. The process of going from analog into digital, we'll talk about it in detail in the next lecture, actually in the second part. The process is called sampling. So you have the continuous time signal and you take samples at certain points in time with uniform spacing. So the spacing between each signal and the other, they are uniform. I think this one here. There you go. So you're having only these values. So they are in discrete time, but continuous value. Now, when you do quantization, you are restricting the values into a certain set of levels. So here, instead of having this value, you probably approximate it to this value, or the sample is here. So this is the value here. So the value in continuous time is here, but you have to approximate it into this value and so on. So you'll do some approximations when you do the quantization. Sampling, you take the exact value of the signal. Quantization, you approximate it to a certain level. Then you can do encoding by converting these values into their binary sequence. For example, the value 6 could be approximated into 110, if you remember, from decimal to binary. Yeah, I'll skip this slide. It's just to show that why people prefer digital over analog, because in digital you have only two values, either 0 or 1, logical 0 and logical 1, and you can set what we call a threshold. If at the receiver part the value is larger than the threshold, I will give it a value logical 1. If it's less than the threshold, that's a digital value 0. So even with the presence of noise, so this signal was contaminated by noise, so I'm receiving this part. At the receiver part, you set the threshold, so you have the bit detection threshold, some point here, almost 0.5, and you can approximate the digital sequence based on that, and so on. So that's just an example of why digital is better than analog. Assuming this signal is analog, you have a waveform like this. At the receiver part, you will receive something like this, very noisy, very hard to recover. All right, also systems could be classified by the number of inputs. You can have multiple input, multiple output, or you have single input and single output. Most of our signals will be dealing with one input, single input, single output. So you have a system like here, X of t, Y of t. All right, so we've talked about the multiple inputs, multiple outputs. All right, so yeah, that's some like another set of classifications. Yeah, I'm gonna skip the slide. Sometimes you have the signal in time domain, you convert it into a sequence, P of n, into discrete domain, do the processing in discrete time system. And once you are done, you convert it back into analog or continuous and go back into YFT. And this is actually the whole field of DSP after this course, inshallah, digital signal processing for computer and communication. This one is not widely used. However, sometimes when we receive a digital sequence, X of n, we want to process it into continuous time systems, probably due to the hardware that is available. So you do the opposite. You have digital to analog converter or discrete to continuous converter. You will have the signal in time domain, do the processing, what you need, convert it back into a digital domain or through the continuous to discrete, and you'll get the sequence Wi-Fi. We've seen that already, the communication systems, all kinds of signals, and this is in control systems, where like a typical feedback system that you have the reference input, you will feed it to the system, you have a controller, you have a plant, and you will get an output. To get the output as close to the reference input, you take a portion, that's what we call a feedback, a portion to the output, do some certain analysis using a sensor, and feed it back to the system. And then you take the difference. So this is a summer or adder. So you make the difference between the reference input and this processed output or sensor reading to get the error signal. Again, that's where you can apply signals and system techniques in the future. So this one in telecommunication, this one in control theory. All right, so I believe this was the first lecture, why it is important, and we talked about this story about building a bridge that was supposed to handle high speeds, but it got collapsed with very low speed. So just an example here. All right, so I did this part for the students who were not here last time, and also to cover it in the recording. We'll be ready to move on into the other part of this lecture. Actually, this lecture is in two parts, A and B. So we'll talk about continuous time and discrete time signals.
This is the last part.
This is the second part of lecture 1. So this is the new lecture. This is what's supposed to be having today. All right. So some definitions. All we'll be dealing with are signals. However, if the signal is continuous in time, if my variable, independent variable is t, we call it a function. If my independent variable is n in discrete time, that's what we'll be calling a sequence. So continuous signals, x of t, discrete signals, x of n. Sometimes we can express them through this one, but this one is the widely used. So example of continuous signals, continuous time signals, that's a typical sinusoid. Sinusoidals x of t are usually modeled by this expression a cosine 2 pi f t plus phi or theta, whatever. So these are the three major components of any sinusoidal signal. We have the amplitude, we have the frequency, and here we have the phase. So phase here will do shift left to right to the signal. Amplitude determine the y-axis values, like the range of values here. Higher amplitude, you will have higher variations. The frequency, the higher the frequency, the closer the signal will be, let's say, to each other. So for example, here, there are no points in time. You're going to determine the frequency. But if this signal is higher in frequency, you'll have something like this. They are closer to each other. I'm not good at drawing, but I hope you get the idea. So that's in time domain. And in time domain, in sequence or in discrete domain, same thing, x of n, a cosine 2 pi f n plus phi. And here is my sequence. Here's my index n. N is restricted to be integer. All right. Let's see, similar expression here. Yeah, that's all we need to know about continuous, sinusoids. Some properties, even and odd. We know even and odd numbers, but what is an even signal? Have you ever heard about that, even signal? Even signal, basically, it's a mirror image of itself, like this one. If you look at the around the y-axis, so assuming that there is a mirror here, and you see an exact reflectance of this part into this part. So this is visually. Mathematically, even signal, you have x of t equals x of negative t. Like you are having the same values for positive time and negative time. Typical example of an even signal is the cosine. For example, x of t equal cosine pi of t. So let's apply at t equal 1. You have cosine of pi. How much? 1 or negative 1? How do you draw it here? Cosine of pi. That's the pi here. It's a negative 1, صح؟ ولا 0 ولا 1?
Right is
Negative 1.
left is -1, then above and down is pi
Okay.
and next to pi.
So pi, you're going this direction, it's negative 1. Calculator, you have calculator? It's negative 1. Now at t equal negative 1. So I have cosine of negative pi. Want to come in? Sure. Okay. All right. So that's an example at cosine of negative pi. How much? So negative pi is like this. Let's try pi over 4 or 1 over 4 at t equal 1 over 4. So I have cosine of pi over 4. How much? هي 1 over square root of 2. كم تطلع؟ 0.707. Okay, did you convert it into radians? All right, that's okay. One of the common mistakes when we deal with pi at the calculator, make sure to convert into radians. 0.707. 0.707. All right, so let's try at t equal negative 1 over 4. Oops. At t equal negative 1 over 4. So I have cosine negative 1 over 4. How much? Did you call? Sorry, pi over 4. Pi over 4. Negative pi over 4. 0.707. 0.707. All right. So in this case, cosine is an even signal. Why? Because I tried the different values of t and always lead to the same value. And if you remember the drawing of the cosine, it starts from 1 something like this. So it is a mirror image of itself over the y-axis. Similar thing, I'm going to focus on the continuous domain because whatever we apply here is applicable in discrete. So an even sequence, x of n equal x of negative n. So it is symmetric about over the origin or around the y-axis. Now, odd signals is another part. You have x of t equals negative x of negative t. So here there is a negation. There's a negative sign. Typical example, x of t sine t or sine pi of t, whatever. Sine of t. Let's try at t equal 30 and at t equal negative 30. Now degrees. Change the mode in calculator into degrees. Sine 30, 0.5. Sine negative 30, negative 0.5. صح؟ You guys memorize the famous angles, sine and cosine. ولا لا?
We took this as a note when we were doing the Fourier series, the Fourier yeah.
Fourier series. You took Fourier series and
When
last
we
math.
did AN and BN and A0, we were taught a trick that basically cosine is even and sine is odd, and basically
The A components or the coefficients of the cosine will be zero if my signal is odd.
Yeah.
All right. It's not a trick. I will not call it a trick. It's something like doing it smart. Like instead of wasting time to find the coefficients at the end, they are zero. From the look of the signal, my signal is even, so I know that the coefficients of the sine parts, they are all zeros, and I'm going to have only the coefficients for the cosine part. Do you know what's the logic of Fourier series? Why did you do Fourier series? What is Fourier series?
Honestly, I'm not.
You've done the math, but what is the
Yeah.
concept? Why Fourier series?
Honestly, don't know.
Okay, so basically for
I know that when we did for the heat, yeah,
heat.
heat
Okay.
equation based on the Fourier series, that basically it's for the transfer of heat and stuff like that.
Okay, Fourier series basically says that any periodic signal could be modeled as summation of harmonics. What do you mean by harmonics? Sinusoidals with different frequencies. That's Fourier series. So a rectangular wave could be modeled by a lot of sinusoidals. But that's the logic of Fourier series. And you have sinusoidals, you have the you have the sine and you have the cosine with weighted coefficients. And your job is to find these weights, the coefficients. There is Fourier series in this course, so we'll go over it. But yeah, not in a practical manner like you mentioned for the heat equation, etc. For any general equation. All right, now odd signals. Basically, you don't have an exact mirror over the y-axis. In fact, you have a mirror over like this imaginary axis of 135 degrees. Like this one is reflectance of that one. This one is reflectance to that one. So let's not worry about this analogy of a mirror image, etc. We have this expression. So when you apply it here, the sinusoidal, for example, you have at 30 degrees 0.5 and negative 30. So when you reverse the point in time, or when you give a negative sign to the point in time, you will get the negative sign and the function itself. And also, if you remember drawing the sign, you start from 0, something like this, and it continue this way. So that's a typical example. Or basically, you can say x of 1 equals how much? 1. X of 2, how much? It is 2. X of 3, I have 1. X of 0 should be always 0. That's a property of odd signals. X of 0 should be 0. Why? It is the origin. It has to cross the origin. So an odd signal must be such that x of 0 equals 0. So if there is a value here, yeah, you cannot assume it's an odd signal. My odd signal should be going through the 0 point. Now, x of negative 1, how much? Go here, that's a negative 1. X of negative 2, I'm having negative 2. X of negative 3, I'm going to get negative 1, which kind of reverse each other. So that's the signal as well. So this is how we do that graphically. Now, every signal in life could be decomposed into an even part and odd part. So whatever signal I give you, you can decompose it into an even part and odd part. Okay, that's another graph for even function and odd function. So that's an example of cosine. That's a sine. That's whatever signal expression graphically, something like that. All right, so check if x of t equals cosine of t is even or odd. I think I've done that already for the cosine, so I'm going to skip this example. You can just say at several points in time, 30 degrees or pi over 4, pi over 2, 3 pi over 4, and negative pi over 4. You can create a table like this. So that's t, and that's x of t. So let's start from negative 3 pi or negative pi. Then 3 pi over 4, negative pi over 2, negative pi over 4. So that's my points in time at 0, then pi over 4, pi over 2, 3 pi over 4, and then we have pi. Okay, now at each one of them, you just find the value. Cosine of negative pi, that's a negative 1. Cosine of pi, I know it's 1. Cosine of 0, that is 1. Cosine pi of 4 over 4, 0.707. Pi over 2, that's 0. 3 pi over 4, negative 707. 0.707. You can confirm the values later. 3 pi over 4, that's a negative 707. And you remember this all sine, tan, cosine. You know what this graph means? Where the value is positive. So this one, all of them are positive. Here is only the sine positive. Only the tan is positive at the third quadrant. Fourth quadrant, only the cosine is positive. All right, so from this table, we found out that these values are the same, and now check if x of t, whether it's even or odd. So simply we can just, similar to this one here, so we have values of t, x of t. So let's try from -3, -2, -1, 0, 1, 2, 3. All right, at -3, I have 0. At -2, I will have 1. At -1, I have 2, 3, 4, 5, 6. So what can we say about the signal? Okay, the condition for odd, this value and this value have to be the same in value but different in sign. Remember, x of t equals negative x of negative t. So this condition does not apply. Also remember, odd signal must have 0 at 0. At 0, I have 3. So it's not odd. What about even? X of -1, does it equal x of 1? ولا حتى even. ولا even. So it's neither even nor odd. Okay? So keep that in mind. All right, let's assume x of t equal 3. Do you think it's even or odd? Do you know how to draw 3? Okay, so it's this line or this line. Okay, horizontal, just substitute. At 0 is 3, at 1 is 3, at 4 is 3, at 10, at infinity is 3. So that's x of t. And that's my time axis. All right, so I plot this function. Is it even or odd? Okay, when I ask you these questions, always go back to the basics. What is even signal? X of t equals x of -t. So this one is always 3. At 1, it is 3. At -1, it is 3. At 2, it is 3. At -2, it is 3. So it's always 3. At positive and negative, so it is an even function. Okay? What about x of t equal t? So how to draw it is this line. That is t, that's x of t. Again,
That's odd.
go back to the basics. Draw this table. At -3, I'm going to get -3. At -2, it's -2. At 0, it is 0. At 1, it's 1. At -1, it's -1. You see, now they are opposite in sign. So it's an odd signal. And notice here, the 3, it's this component. The t, it's this component. So this function is neither even nor odd. However, the even part is 3 and the odd part is t. Now we'll see the method how to find these components. I told you, we will decompose the signal into even component and odd component. All right, so some key components here or key concepts, I don't want you to memorize, but it says that if you have an even function, you multiply it with an even function, you will get an even function, the result. When you have an even function multiplied by an odd function, the output will be an odd function. Now don't confuse it with math. When you have an even number, you multiply it with an odd number, you will get an even number. Like 2 times 3, it is 6. 2 is even, 3 is odd, 6 is even. That's in math. In functions and signals, when you multiply an even signal by an odd signal, the output will be an odd signal. Now, when you multiply odd and odd, you will get an even signal. Unlike math, when you multiply odd by odd, you will get odd. 9 times 9, that's 81. Odd times odd, it's odd. But in signals, it's a bit different. Summation of functions, even plus even is even plus odd, it's neither. And that's an example here. I have the even part, I have the odd part. When I added them together, it's neither. When you have an odd function added to an odd function, the result will remain an odd function. All right, so how to find the even part and odd part of any function or sequence given? Basically, you run this expression. I have f of x, so that's in terms of x, but in our case, if I want to write it like this, x even of t equals x of t plus x of negative t over 2. So this is how we extract the even part. For the odd part, x odd of t equals x of t minus x of negative t over 2. And this is, we mentioned that already, x of t always is the composition or the addition of x even of t plus x odd of t. And this one we can generate every function. So let's see some examples here. So that's visualization of even and odd functions. Similar thing here. This one just says an integration. When you do integration of an even function, instead of doing it twice, you do it for half of it and you multiply by 2. And you've seen that probably in advanced math when you integrated the cosine. Instead of integrating from negative pi to pi, you integrate from 0 to pi, then multiply by 2. In odd functions is a bit different. In calculus, you calculated areas, right? In calculus. In areas, the areas that under the x-axis, you multiply it by a -1. You give it the absolute value because your physically area should be positive. Here, we are not limited by physical constraints. We're not talking about areas. It's just integration. Now, when you integrate an odd signal for a full period, like the sine signal, integration of negative pi to pi sine of t dot dt, this is odd signal, and I'm integrating over a full period, that's going to be 0. Or similarly saying that if I integrate from similar points in time from -a to a for an odd signal, the result will be 0. Because basically I'm going to have negative value here, that will cancel out this one. I have this value here, it will cancel out this one. This value here, cancel this one, because they are similar in shape, similar area, or similar value, but this one will give me a negative sign, this one will give me a positive sign. Same in value, but different in sign, they will cancel each other. Same thing here, positive value, negative value, same in value, different in sign, they will cancel each other. All right, so this is one just show you like one of the shortcuts when dealing with integration of even and odd signals. All right, so this one is talking about periodic signals. Let me give you an example of decomposing a signal into even and odd. Okay. Okay, assume that you are given this function x of t equal x square t square minus 3t plus 10. And find x even of t and x odd of t. All right, so x even of t, formulas will be given, but I know it's x of t plus x of negative t over 2. X of t, the function itself, t square minus 3t plus 10 plus x of minus t. So substitute minus t here. So I have minus t squared minus t squared minus t squared. Okay, t squared. I know that some of you like, is he for real asking for this? But yeah, it is for real. I'm asking for this. I'm going to give you another example. I want you to solve it in the notebook. Why? I noticed like when I describe things, they sound easy. Some students, not all, they struggle of finding this one. So I want to see these cases now rather than the quiz. Okay. So x of negative t. So for each t here, I'll substitute negative t. So I have negative t squared, that's t squared. I have negative 3t times negative t plus 3t. 10 is 10. It's plus over 2. So that's x even of t equals this. T square and t square, 2t square. Negative 3t plus 3t, they cancel each other. 10 plus 10 over 2. So that's t squared plus 10. All right, x odd. X of t. X of t minus x of minus t over 2. So x of t, I'll write it as it is, t squared minus 3t plus 10 minus. Now x of minus t. We've done that already here. It's the same expression. So t squared plus 3t plus 10 over 2. Then distribute the negative sign. So I will have okay. So let's distribute. I have t squared minus 3t plus 10 minus t squared minus 3t minus 10 over 2. T squared and t squared will cancel. Negative 3t and negative 3t, negative 6t. 10 minus 10, that's a 0 over 2. So those are the even and odd component. You want to confirm, add them together, you should get the original function. So I have my even part here, and that's my odd part here. And if you go up, that's the function here. Actually, from the look of this function, t squared, how to draw it? So that's even. 10, that's even. Now the negative 3t, it's something like this. Decaying function pass through the 0, that's the negative 3t. That's the odd part. All right, I want you to try this function. X of t equal 3t squared plus 5 cosine t minus sine 2 pi t plus 10. Okay, from the look, what is the even part? All right, and the odd part. Look at each function individually, and you'll know which one is even, which one is odd. But in exam, I won't see the solution. But like a hint, you can say, oh, all right, this is even, this is odd. Like you can confirm the answer by looking at it. Find the even part. Find the odd part. أنا عشان طلع لا يكتب الله كاستوديو الألعاب تقنية أو الأسماء الاستوديو كنت هون سنة أنا ماشي بالعكس يوم كيف بس أنا مش هو بعد ما كنا كاس الشغلة الثانية صرت هي هذا يعني تحت صوت مايس أو just the two mics مش شو يعني شفنا الكوساين نيجاتيف 2
I was it's fine. It will come out.
شو
إذا كان ضيع في البحر.
هلا نحن all right. Okay, so for such questions, start with finding x of negative t equal 3 negative t squared plus 5 cosine negative t minus sine 2 pi negative t plus 10. That equals negative t squared. It's going to remain t squared. The negative will be gone with the square. So I have 3t squared plus cosine of negative t. We know from the cosine properties that cosine of negative angle equals cosine of the angle itself. So the signal here will be gone. The sign, the negative sign. So I have 5 cosine of t minus. All right, now I have sine. So sine of t or sine of negative t, we know from the sinusoidal properties is going to equal negative sine of t. So I'm negating the angle here. The whole thing will become negative sine 2 pi t, all right, plus 10. So 3t squared plus 5 cosine t plus negative by negative is plus sine 2 pi t plus 10. So that's x of negative t. All right, now x even of t equal x of t plus x of negative t over 2. So we'll copy x of t as it is. I have 3t squared plus 5 cosine of t minus sine 2 pi t plus 10. Plus, I'll take this expression, 3t squared plus 5 cosine t plus sine 2 pi t plus 10. All this over 2. All right, so I'll keep the fraction over 2. 3t squared and 3t squared, that's 6t squared. I'm doing the dash, so I do not consider them later to avoid confusion. 5 cosine t, 5 cosine t, both the same sign, so that's plus 10 cosine t. All right, so I have negative sine 2 pi t, positive sine 2 pi t, they will cancel each other. 10 plus 10, that is a 20. Then divide each number over 2. I will have 3t squared plus 5 cosine t plus 20. So that is the even part. All right, the odd part, similar approach, x odd of t equal x of t minus x of minus t over 2. And I will get 3t squared plus 5 cosine t minus sine 2 pi t plus 10 minus, then I will put the expression of x of minus t. I will have 3t squared plus 5 cosine t plus sine 2 pi t plus 10. And all of this divided over 2. Now distribute the negative sign. So I'll copy this as it is. 5.
Be the same answer for the.
No, they can never be even and odd. They can never be the same. Sine 2 pi t plus 10 minus 3t square minus 5 cosine t minus sine 2 pi t minus 10 over 2. Now it's simple here. I have 3t square and negative 3t square. They will cancel each out. 5 cosine t, negative 5 cosine t. I have negative sine 2 pi t, negative sine 2 pi t. I have negative 2 sine 2 pi t. All right. And then I will have 10 minus 10 over 2. Then my answer will be negative sine 2 pi t. And that is the final answer for this question.
In order we change all the numbers to negative.
Not change t into negative and substitute in the function itself. So my function, the original function is this one. Find x of negative t. So here for each t, I substitute negative t. So I have negative t squared cosine negative t sine 2 pi negative t. 10 is 10 is a constant. And then work out the algebra, the math to get the final answer. So I have x of negative t. Then for the even part, you add x of t and x of negative t plus divides over 2. For the odd part, you have x of t minus x of negative t, then divide over 2. Yeah, for even and odd, to find the even and odd parts. There you go. But those as, let's say, as function, like f of x. But I wrote a while ago in terms of x of t. All right, so let's talk about periodic signal and how can we find the period of a signal. Okay, so what is a periodic signal? It's basically a signal that repeats itself over a certain point in time. So a function x is said to be periodic with a period t or t periodic for some strictly positive real constant t. The following condition holds: x of t equals x of t plus uppercase t. A typical example, the sinusoidals. They are periodic over how much? What is the period of cosine of t? When the sine starts repeating itself, after how much? Let's say if I draw the sine. This is a sine. Okay, assuming a proper drawing where the signal starts repeating itself. If I'm starting from here, where is the other point the signal starts repeating itself? This one? This one? There you go. Why? I moved my finger, drawing here, done. Now I'm repeating the same thing. Now if I continue, so that's my other side, my other, let's say, cycle of drawing and so on. So what is that value? That's all t. So this is a sine of t. If I'm telling you this is a function sine of t. All right, so what is the value here? And what is the value there? That's a 1. That's a negative 1. We know that sine always goes from negative 1 to 1. What about now where it has its peak? What is this point in time? What is the value of the angle t that will give me sine of t equal 1? When is the sine equals 1? When the angle is ولا هي من الزيرو؟ احنا على الزيرو. اها باي اوفر 2 وهاي الباي وهاي 3 باي اوفر 2 وهاي 2 باي. تمام. يعني it's a sinusoidal. All sinusoidals are periodic over a full period of 2 pi. هلا أنا said it's sine of t, but if it's sine 10t it will be different. ليش؟ لأن الsignal will be having higher frequency. We'll talk about these signal manipulations later. So this sinusoidal signal, this sine is periodic over 2 pi. What does that mean? Every 2 pi, the signal starts repeating itself. So the first period, 2 pi. The second period, 4 pi. Third period, 6 pi. And so on. So notice here, now my other replica is from 2 pi to 4 pi. You know what replica means, right? Replication, النسخة الثانية منها. Here, that's a 6 pi. So it says here that x of t equals x of t plus 2 pi. And if I said here x of t equals x of t plus 2 pi in this sinusoidal. Now substitute any values of t, this expression will hold. Why? Because the signal is repeating itself over 2 pi. And for example, this one here, that's a pi over 2. What is the value here? Pi over 2 plus 2 pi, that's 5 pi over 2. On pi over 2. Is it كمان 2 pi? I will say it's 9 pi over 2. And so on. Or graphically, something like this. In general, not just sine or cosine. This signal, let's see, if I want to start from here and starts repeating itself into there. So this is a full period. Or you can say, all right, I want to start from here and end from here. Full period. They both have to be the same because the same function, but I'm taking different points in time. So it's the same period. If you want to start from here and you finish here, that's the period. So what I'm saying is you can pick any point in the function and look to the similar point in the other image, in the other replica, let's say, and that will be your period. So you can take any point. It doesn't have to be, oh, I need to start from 0, is this point, then I have to start this point. Usually the best way to find the period, look either at the peaks or the bottoms. Look at the peaks. So here, from peak to peak, that's one period. From peak to peak, that's one period. Or from bottom to bottom, that's or another peak, that's a period. Tamam? So in this expression here, they decided, okay, I want to take from this point into this point. So that's the period t. And discrete signals is the same. You look, let's say, you start from this point. Where is the other image? This point. So from -2, -1, 0, 1, 2, this period is 4. So it's repeating itself every 4 points. All right, so a t periodic function, x, is said to have a frequency 1 over t and an angular frequency 2 pi over t. Now, have you heard of angular frequency? Omega, lowercase omega. You've done sinusoids before, صح? So you either write sine 2 pi ft or sine omega t. Omega equal 2 pi f. This one, the unit is radian per second, and this unit is hertz. 2 pi is unitless. So angular frequency, radian per second, omega, and the frequency f is hertz. And both of them, they are frequency. Some references, they prefer omega. Some references, they prefer f. That doesn't change the fact the theory is the same. It's just a little bit of mathematical modeling. Now, mathematically, f, the frequency, equal the reciprocal of the period, 1 over t, mathematically. So in this case, 2 pi it says that the frequency omega 2 pi f 2 pi over t, that equals to omega. And angular frequency, it is omega. Now that's for continuous signals. What about periodic signals? There is a restriction. So continuous signals doesn't matter. T could be any value, uppercase T, that's the period. It could be any value. Now in periodic signals, if you remember here, or if you have seen in this graph, notice what about these values? They are all what? Integers. So in periodic signal, it is the same. A sequence X is said to be periodic with n or n periodic f for some strictly positive integer. By the way, the period is positive, frequency is positive. They are physical values, they are positive. But in the period in continuous signals, could be any value. In discrete signals, it has to be integer. So yeah, if you want to compare both the statements for some strictly positive real constant, for some strictly positive integer constant n. And the following condition holds. Similar thing here with t, and you have dealing with n. So an n periodic sequence X is said to have frequency 1 over n and angular frequency 2 pi over n. So a function or sequence that is not periodic is said to be aperiodic. This A is what we call a prefix to negate the word. So periodic, aperiodic is not periodic. All right, so graphically we have seen that the signal starts repeating itself after a certain cycle. You can pick any point in the function or the sequence. You look where the signal starts repeating itself to that other point, and the distance between these 2 points is the period. All right. One thing about periods of signal, they are not unique. Like it could be periodic over multiples of the main period, or what we call a fundamental period. For example, if I go back to my cosine here. So I said, okay, it repeats itself over 2 pi, right? What if I said, okay, I'm going to continue drawing, and I can say that the signal starts repeating itself every 4 pi. And notice this segment is exactly similar to this segment. And it's going to be exactly to a third segment. So the period here could be 4 pi. It's still fine. You can consider it as a 4 pi. But to differentiate any other period with the original one, like what we call a fundamental period, we call this one as fundamental. Like that's where the function actually starts repeating itself. But the function is still, like just a statement saying that the function is periodic over multiple periods. So you have the fundamental period and you have multiples of the fundamental period. You can say the function is periodic over these periods. So this example here, instead of saying I want from this peak to this peak, I want from these 2 peaks to these 2 peaks. So that's 2t. So the standard one, fundamental one, is t. So period, if a periodic signal is not unique, that is a signal that is periodic with period t is also periodic with multiples of t, period kt, for every strictly integer k. So the smallest period with which the signal is periodic is called the fundamental period, and it has a fundamental frequency, which is the reciprocal of the fundamental period. All right. Determine if the following signals are periodic. If a signal is periodic, determine its fundamental period. All right, so let's look at the first one. X of t equal cosine t plus pi over 4. First, we know by fact that cosines are what? Or sinusoidals are what? Periodic. They are in nature periodic. So this one is periodic signal. What is the fundamental period? Remember, cosine general form equals a cosine 2 pi f t plus pi. Now compare these two together. So I know this is my phase shift, Has nothing to do with periodicity or if the signal is periodic or not. It's just a phase shift. So I can exclude this value. I don't have to worry about it. Now, what about amplitude? So it is a 1. Now I have this one, 2 pi f. I have t. So what can we do? How to find f? Or if you want to write it in a way, 2 pi over t, so that's like another expression of frequency, 2 pi f or 2 pi over t. So how much is 2 pi over t? Here I have t equal 2 pi f t. T and t will cancel. I have 1 equal 2 pi f. So here f equal 1 over 2 pi. ومن t how much? The reciprocal del f 2 pi. Honestly, be honest. Do you know what I did here? لا. Okay, I'm comparing this expression with this expression. That's the general form of sinusoids. A cosine 2 pi ft plus theta or phi, phase shift. When I did the comparison, A is 1. So I have cosine t plus pi over 4. That should equal A cosine 2 pi f t plus pi. Now just compare the terms. So here I have nothing. That means it's a 1. So A is 1. The amplitude equals 1. Cosine and cosine. What if it was a sine? It's the same thing. Like if it was this sine, the general expression is sine. Cosine and sine, they have the same general expression. أو إنه إذا بدك زي هيك 2 pi over t, you mean like this? Two pi over 1.
2 pi over t, it's the frequency for
So instead of writing 2 pi f, you can say 2 pi over t. يصير it's fine. So you can say A cosine 2 pi over t plus phi. صح? Yeah, you can do that. ليش؟ لأنه previously we just said that f, the frequency, is t, or the angular frequency 2 pi over t. وزي ما حكينا omega equal 2 pi f equal 2 pi over t. Okay, so let's go back to the question. We determined that the amplitude is 1. What about the phase? Phi. Compare. I have phi here. We have pi over 4. And notice those are not. La. They don't have to be equal, but they are not what I wanted. What I wanted is the frequency or the period. But I'm just comparing two sinusoids together. All right, so I have this term and this term. They both have to be equal. So I have t equal 2 pi over t times t. هلا ليش انا بحب انه نستخدم الاف؟ لانه في عندنا تي هون، في عندنا upper case t تو هون. في ناس it might confuse some people. upper case t, lower case t, they all sounds t. So when I say it 2 pi over t times t, so if it's not written it might get confusing. Let's keep it 2 pi f, but still this is perfectly fine. 2 pi f t. All right, so I have t and I have t. Divide over t. T times t, that's 1, equals 2 pi f. So f equals 1 over 2 pi. Tamam? All right. Now the question is asking what? If the signal is periodic, we say this periodic is a sinusoidal signal. Find the fundamental period. Fundamental period, find t. So I found the frequency. What's the relationship between frequency and period? F equal 1 over t. So I have 1 over t equal 1 over 2 pi. So if those are the same, then those are the same. So here t equal 2 pi. All right. This one is similar. Try to solve it on your one. C and D, we'll solve them all. Try B. صار انت مع ثلاثة.
It's 1/3. So
Okay, to avoid time constraints, I think we still have about 10 minutes. So here I will have sine 2 pi t over 3 equal a cosine 2 pi f t plus phi. I don't have any phase, so this one will be gone. There are no value for amplitude, so this is 1. So I have 2 pi t over 3 equals 2 pi f t and t will cancel. 2 pi and 2 pi will cancel. So I'll have f equal 1 over 3. So t equals 1 over f equals 3. All right. Number C or letter C, x of n equals cosine 1 over 4 n. Again, a cosine 2 pi f n plus theta or phi. So there's no phase shift and amplitude is 1. So I have 1 over 4 n equal 2 pi f n. So here n and n will cancel. I will have 2 pi f equal 1 over 4. F equal 1 over 8 pi. So remember, it's a sequence. We will not use uppercase T, we'll use uppercase N. N equals 8 pi. What is your comment in this one? Is this periodic or not? Okay, I found it. It's like you can say it's first of all, it's cosine, should be periodic. And I'm getting the fundamental period, N equals 8 pi. So we can stop right there. But what is the last thing we said, huh? There is a restriction on n. Again, and t continuous could be any value. What about n? Integer. Let's go back here. n equals 8 pi. Is this integer? لا باي احنا بنعرف انه it's a rational number. So it is not periodic. Even though it's a cosine, it sounds periodic to us, but because n is not periodic, we cannot say it's a periodic signal. Tamam? Now let's check this one. X of n equals a to the power j pi over 4n.
Sine
أيوة
pi over 4 n
plus j sin هاي شو اسمها هاي؟ لما يكون عندك complex exponential you convert it into cosine plus j sin. Euler identity. شو الأويلر identity؟ ما في عندنا مساحة. I'll write somewhere else. Discard. So the question was x of n e to the power j pi over 4n صح؟ So e to the power j alpha in general cosine alpha plus j sine alpha. هاي Euler identity. عمركم سمعتوا فيها؟ والله سيركس 2 أخذتوا سيركس 2؟ Okay, I will provide it. Euler identity, I will provide it. All right, so I have cosine pi over 4n plus j sine pi over 4n. No, I know cosine and sine, they are periodic. I need to find the fundamental period. But if I did it for cosine, do I need to do it for sine? If I did the question, if I solved it for cosine, do I need to solve it for sine? ليش؟
because in this case it's gonna give us we know both of them are basically it's like the thing with even and odd.
Okay, but one of them is
They're both
complex.
periodic.
Okay, both periodic.
So if we find the result for one, it should be the same for the other.
Okay, you are half correct. Now, why I can do that? Because they have the same frequency. Sine and cosine, there's only phase shift between them by 90 degrees, pi over 2. So if I do it for cosine, I can make the same assumption for sine. Again, they both have the same frequency or the same component here. Now, what's cosine and sine? So this one, I can simply make it j sine pi over 4n plus pi over 2. It's a phase shift pi over 2. So let's work on the cosine. This one, we'll leave it. We can make the same conclusion for that one. So again, pi over 4n equals 2 pi f n, and n will cancel. Pi and pi will cancel. So f equal 1 over 8. منه n equal 8 periodic. تمام؟ All right, so let's continue. Oh, well, there is plenty to do. Sampling. Yeah, we'll talk a little bit about sampling. We'll continue next lecture, inshallah. Okay, slideshow. So what is sampling? It's the process to go from continuous domain into discrete domain. All right, so often we want to be able to convert between continuous time and discrete time representations. Let me duplicate. So we have the process sampling and interpolation. Let's not worry about interpolation. So sampling is performed by a continuous to discrete converter or analog to digital converter. Interpolation will do the opposite. You have discrete, you want to go back to the continuous. And that's a thing about sampling is not invertible. That means that if I have x of t, and created a sequence R at x of n, I cannot simply go from x of n to go back to exactly x of t. There'll be some differences, some terms. So it's lossy kind of process. You will lose some information. Okay, so sampling usually is periodic. It means that I take samples at a fixed point in time. I'm taking, let's say, every 10 milliseconds or 10 to 20 milliseconds and so on. So here the sampling is uniform. So for example, if I'm taking samples every 10 milliseconds, so here I have the first sample, second sample, third sample, fourth, etc. Now by indices, I will stop using 10, 20, 30. My samples are integer values. So it's 0, 1, 2, 3, 4. So these are my indices.
So, is it, has to be squared, right?
أيوة.
Even the slightly.
With this scheme, a sequence of y samples obtained from a continuous time signal x according to the relation y of n. Okay, so this one should be like this, but this one is still fine because x is the continuous one, but y should be the discrete one. Okay, as a matter of terminology, we refer to t as a sampling period with the sampling frequency 2 pi over t. Actually, we call it t of s, so showing that it's sampling period. It's not the same period of the signal, it's different. An example of periodic sampling is shown below, where the original continuous time signal x has been sampled with sampling period t equal 10. By the way, this one also will call it t of s. Now t of s given constant. I want to sample every 10 milliseconds. So how to do sampling? Simply, you can fill a table. This is n, and this is x of n ts. So if I have 0, then I'm going to take x of 0. I have 1 x of ts, 2 x of 2ts, 3 x of 3ts. Now let's assume ts is 10, like in this example. So y of 0 is going to be equal x of 0. Y of 1, my first sample, is going to be x of 10. So I go here, x of 10, this is the value. So that's my second sample. Y equal 2, I'm going to take x of 2 times 10, x of 20. So that's my third sample, and so on. So in the exam, whether it was midterm quiz or something, expect something like this. I'm going to ask you to do the sampling process with a certain given sampling period. You will be provided, and write the first 5 samples, for example, and just do a simple table like this. All right, so it's not invertible in the absence of any constraints. So yeah, like t of s, the sampling period, could be any value. However, there are some constraints to at least like recover the signal or get some representation that is similar to the original signal in time. For example, if you have x of t equals 2 pi t, like in this one here, and you said I want to sample every pi, like every multiples of pi. So you have x of cosine of pi, sorry, sine of pi 0, sine of 2 pi 0, sine of 3 pi 0, sine of 4 pi 0. You are taking samples, but you're taking what? The 0 samples. So you're not getting any information from the signal. All right, also, when you have a signal like this equals 0, but doesn't matter how many samples you have, it's always 0. So it's useless to have sampling in such signals. So if we sample each of these signals with a sampling period t equal 1, we obtain the respective sequences, yeah, like multiples of pi. You get zeros everywhere. And give us continue next week, inshallah. So let's stop here. Stop sharing. Stop. Please, every lecture, remind me to start the recording. I may forget. And sharing the screen also. So more, record, stop, recording, stop.